Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem minimize deviation in array. This one is going to blow your mind. So we're given an integer array, maybe something like 1, 2, 3, 4. The rules are pretty simple this time. If a number in the input array is even, then we can divide it by 2. We don't have to, but we can. If a number is odd, then we can multiply it by 2, but we don't have to. Now our goal though is to minimize the maximum deviation. The deviation is defined by taking the minimum element in the array and the maximum element in the array and getting the difference between those, which in this case is 4 minus 1. Now, if you read this problem, they describe the deviation differently, but I think they're trying to make it more complicated to confuse you. They say it's the maximum difference between any two elements in the array. That makes it sound like you have to compare every two elements in the array. You don't have to. You just need the minimum and the maximum. Now, even knowing that, this problem is still pretty hard because there's so many things we could do. At least that's what it seems. Like we have a 1 here, so we can choose to multiply it by 2. We could take this even number, divide it by 2. We could take this odd number and multiply it by 2, this even number and divide it by 2. And after we do those operations, maybe we can do even more operations. So how do we figure out how to minimize the maximum difference? Well, obviously, us changing maybe like the 2 or the 3, that's probably not going to decrease the difference between 1 and 4. If anything, that'll end up increasing it. Maybe if we make this a bigger number like 5 or something, then the maximum difference is even bigger. So probably we want to operate either on the minimum or on the maximum. So that's one observation, and this is probably the trickiest observation that you have to make. There's a pattern to how we can multiply and divide these numbers. Let's take this odd number. We can only multiply odd numbers by 2. So now let's multiply it by 2. What do we get? We get a 2. Let's take this odd number, 3, and multiply it by 2. What do we get? We get a 6. Any number, whether it's odd or even, multiplied by 2 is going to be an even number. It's kind of in the definition. It's going to be divisible by 2. I mean, 2 is clearly a factor of whatever number this is going to be. This is not really programming. This is just math. So what we learned is anytime we take an odd number, the only thing we can do with it is multiply it by 2, and then we can't do anything with it ever again. So for every odd number, the range of possible values that this could be is going to be either 1 or 2. For the 3, it's going to be either 3 or 6. Now things get a little bit different with the even numbers. With even numbers, remember, we divide them by 2. What happens with 2? We divide it by 2, we get 1. Can't really divide it any further. It's an odd number now. So now the only thing we can do is multiply it by 2. What happens when we multiply 1 by 2? We get 2. Well, that's what we had over here. So the possible range of values for this guy is actually the same as this guy. What about the 4? When we divide it by 2, we get 2. Divide it by 2 again, because it's still even, that's all we can do, we get 1. Now, is there going to be a pattern with even numbers? Not necessarily, because if we get an 8, we can divide this by 2 4 times. And if we get a 16, we can divide that 5 times, and we can get a 32 and then divide that. So with even numbers, we could get a long chain of divisions. But take a look at the list. They're still going to be discrete. Like, it's not going to be infinite. They're going to end at 1 or before that, actually. For example, a number like 6 divided by 2, we get 3. Can't divide it any further. It's an odd number now. We can multiply it by 2 and get back to 6. But other than that, can't really do anything. The point is that each number has a defined list of values that it could be given these rules. Now, on top of that, we have to make another key observation here, and that is that each of these numbers, there's a possible set of values it could be. We know that all these numbers are positive, so the lowest possible value, let's say they could be, is 1, but there is some upper bound here, And there is a max value for the integers in this input array. It's something like 4,000 or something like that. So it isn't like a massive integer, but let's just say this is like n or some max integer. This guy is going to have a range of possible values. In this case, it's 1 and 2. 2 is also going to have a range of values. It just happens to have the same range of values. 3 is also going to have a range of values. I believe it's going to be 3 and 6. 4 is going to have a range of values. I think it's 4, 2, and 1. So when we visualize it as a number line, it becomes a bit more simple. Not super simple, but a slightly more simple, because now we're just trying to minimize one of these. But actually, not necessarily one of these, because for any possible set, like we need to include all 4 values, because remember what we were trying to do is get the difference between the minimum and the maximum. So we can't just say, okay, get the minimum between these two, because we need all 4 values. For example, maybe this, because this includes all 4 colors. So in this, what is the minimum difference? But I guess even like this, it's kind of hard to solve. How do we compare every pair of values, and how do we know if all 4 values are in a set? This isn't simple either. But since we know that every value will have some type of lower bound, why don't we take every initial value and try to minimize them? What I mean is, if this is the initial value for 4, let's try to minimize it as much as we can. Try to push it all the way over there as we can. And let's do the same thing for purple. Well, purple is odd, so we can't minimize it. We can increase it, but can't minimize it. So we'll leave this here. And with green, we can minimize it once. And with red, we just leave it there because it's odd, so we don't want to maximize it, so we leave it there. So quickly, I'm going to take this red, put it over here. That's the minimum. Take this orange and also put it over here. That is the minimum. Now, among all of these minimum values, how do we find the maximum difference? Well, we would just take the maximum and the minimum. In this case, we can choose from any of these and then get the difference. So here, I think it's going to be 3 minus 1, which is going to give us 2. But how would we do that? Because we still have an array of 4 or n elements. And to find the min and the max is going to be a linear time algorithm. So can we do it faster? Yes, we can. What we're going to do is we're going to keep track of the maximum value. We're going to have a separate variable for that. And every value, meaning every value like in the array, once we've taken each of these and minimized it, is going to actually be pushed to a heap, specifically a min heap, because if we're keeping track of the maximum, then we can just pop to get the minimum, or just look at the top of our heap. But we're going to want to pop because we specifically want one of these minimum values, because just like I talked about at the beginning, the only way we're going to decrease the maximum difference is by changing either the maximum value or the minimum value. We already took the maximum value and tried to make each of these as small as we possibly could, so we can't really take any of them and make them smaller, but we can try to take the minimums and make them bigger. That's what we're going to try to do. So since all of these are the same size, we can pop any of them, but what we're going to do is pop one and then multiply it by 2, because odd numbers can be multiplied by 2. So then the orange is going to go over here, but we're still going to end up popping from the minimum. Our maximum is not going to be changed. It's still going to be 3, but we're going to be popping from here. And for each of these two, we're going to do the same thing, pop each of them and then multiply it by 2. Same for this guy, pop it and multiply it by 2. Now we get to a point where we have 3 of the values over here and the last one is over here. Now we're going to pop one of these and we're going to get a new minimum difference, because these are now at 2 and our maximum so far is at 3. The difference between them is going to be 1. So that's going to be our new minimum. And we're going to keep continuing this algorithm until each of these guys is at its maximum possible spot. So for the green one, we know it was 2, so it's going to end at 2. For the 1, it started at 1, but odd numbers can be multiplied by 2, so it's going to end here at the 2 value. Because then with an even number, we can't really multiply it by 2, we have to divide it by 2, and then we're just going to get stuck in an infinite loop. So we're not going to do that. And finally, with the orange one, it actually started at 4. So if we multiply it by 2, we're going to get 2. But with a 2 value, we can't multiply it by 2 again, but that's a problem because it's possible that we'll miss an answer because 2 was 4. That's its original value. It should be able to get back to 4. So I'm going to take care of this in the code, but I think this is probably getting really complicated at this point. So I'll just make a couple more points. The most important one is, how long are we going to continue this? Until the heap is empty, maybe? No, we're going to continue this until the heap is less than the original size of the array. Let me show you why. Let's say this red value 1, it's originally 1, but we end up multiplying it by 2, and then it gets over here to the 2 spot, and then it can't really go any further. So maybe it is the minimum value. Maybe we popped all of these, and maybe there's some values over here, but then we want to pop this guy as well. We pop it, and we see we can't do anything with it, so we're not going to push it back to the heap. So it's not going to be on our number line anymore. So now should we continue? We only have 3 values left on our number line. We should not continue. Let me tell you why. We're trying to take the difference between the min and the maximum in the entire array. We can't just choose to selectively ignore values. That wasn't part of the rules. So if we just ignore this guy, we're not going to get the correct answer potentially. So at this point, we would stop our algorithm. But is it possible we're going to miss a solution because we're stopping too early? Definitely not, because remember, we took all our values, pushed them as far left as we could, and now we're trying to push them to the right by prioritizing the minimum values, and we found a minimum value we can't push to the right anymore. Maybe we can keep pushing these guys, but this one is stuck over here. So if we take this, push it over here maybe, then to find the maximum difference, we would have to take this and subtract this one. So it would basically be like this. So clearly, as we push these guys to the right, we're not going to be decreasing our maximum difference. We're going to be possibly increasing it. So we're definitely not going to miss a solution by doing it this way. This has gotten really complicated, so I'll talk about the time complexity after we code it up, which is going to be now. So first I'm going to initialize our min heap, and I'm going to keep track of what the maximum value is in our heap. So initially I'm just going to set that to 0, but remember that's going to be important for actually finding the maximum difference. Next, I'm going to initialize our heap, but remember how we're doing it. We're going through every number in the input array, but before we can append n to the heap, we have to try to minimize it. We know that odd values can't really be minimized because we can only multiply those by 2. But if a number is even, which we can check just like this, then we're going to divide it by 2. So you can do that like this in Python. And then we're going to append it to the heap. But remember that catch I was talking about. When we take a number like 2 and then divide it by 2, we get to 1. When we take a number like 4 and then divide it by 2, we get to 2, then we can divide it by 2 again and we get to 1. Now, these are the minimum for each of them, but we should be able to take 1 and multiply it by 2 to get its original value. We should be able to do the same for this one, multiply it by 2 and get to 2. But at this point, we would stop because usually with even numbers, we don't multiply them by 2. But we know that this one had an original value of 4. We should be able to get back to that if we want to find the solution. So we're going to actually keep track of every number's original value. So when we append n to the heap, we're actually going to append 2 values. We're going to append a pair, n, and its original value, which I'm going to get by saving it in a temporary variable called temp. So now we're going to append temp here. But we actually have a problem here as well, believe it or not, because what about if we just started with a value of 1? In this case, with our heap, we would append 1 and the temp, which is its original value, which is also 1. But we know a 1 odd numbers can be multiplied by 2 to get to an even number. So with 1, we would want to actually here append 2 times temp. So here we would actually want to append 2 times the original value if it remains unchanged, which will always be the case for odd numbers. That's why we're taking the original value. So here, instead of appending temp, I'm actually going to append the maximum of temp and the original value multiplied by 2. Anytime we have an even number, we're going to end up dividing it by 2 at least once. So this will end up appending 2 as well as temp. But if we have an odd number, it's never going to be divided by 2. In that case, it's going to end up appending n as well as 2 times n. That's kind of the maximum it will ever be. Pretty complicated stuff, but this is a Leetcode hard for a reason. So now let's get into the actual heap. Oh, I forgot up above, we are going to be getting our heap max as well. The best way to do that is just to continuously get the max of itself as well as whatever current number we're at. And we do want n in this case because we actually want what value is in the heap. We want the actual value in the heap. That's what's going to be used as the heap key. So now let's initialize our result. I'm going to set it to a really big number because we're trying to minimize it. And then when we created this heap, we actually didn't make it a heap. It's just an array right now. So to turn it into a heap, we can say heap q.heapify, run that on the min heap. Now we're actually ready for our loop. Remember, we're not doing this while the min heap is non-empty. We're doing this while the min heap is the same length as the input array nums. And then we're going to pop from it. So heap q.heap pop from the min heap. And the values we're going to get from it are n and the maximum that this value can possibly be, that pair of values that we ended up adding. Every time we pop a value, we want to possibly update our result. We already know what the max is. We are saving that in a variable, and we can subtract from it n. And it's possible that this will be a new result. We'll only know if we take the minimum of the current result and this and possibly update it. Now, every time we pop a value, we possibly want to append 2 times that value back onto the heap. But we're only going to do it if the max possible value of it is actually greater than the current value. That means we can multiply it by 2. So we're going to check exactly that. If n is less than its possible maximum, then push to the heap that value n multiplied by 2. But don't forget, we have a pair of values on that heap. We're not just storing a single value, so let's make this a pair. We're going to store the original value multiplied by 2. That's the first value. And the second value is just going to be what its max was. That's not going to change. The maximum it's allowed to be is not going to change. So we're just going to append the same value. Though it's possible that now we have updated our maximum. If we're appending 2 times some value, it's possible that the heap max is now an even greater value. So let's possibly update it with n times 2. So now our loop will keep running until we pop an element from the heap for good. And at that point, we can't come up with a better solution. So we will end up returning our result. So now let's run the code to make sure that it works. And as you can see, yes, it does. And it's about as efficient as you can get. But don't let the Leetcode runtime confuse you. In terms of big O time complexity, this loop over here is going to run in big O of n. Let's say n is the number of elements in the input array. Appending here, we're just appending to an array, so that's not going to take any time complexity. But here we have a while loop. Now, how many times can you take a number and divide it by 2 until it equals 1? Well, that is the logarithm function, but we're not going to be log nning because n is the size of the array. Here we would say log maybe m, where m is like the max possible value in the input array nums. So for a number like 16, how many times can you divide that by 2? I think it's 4 or 5. So log of 16 would be something like 4 or 5. The time complexity down here, though, is a bit different because even though the size of our heap is always going to be n, And popping from a heap of size n is going to be log n. How many times are we going to pop from it? Are we going to pop n times? That would be n log n. Not necessarily, because we might take the same value, pop it from the heap, and then push it back. How many times are we going to push it back? Well, same number of times as this. In the worst case, at least, when we take a value and keep dividing it by 2, then in the opposite case, we're going to take that same value and keep multiplying it by 2. So here, the time complexity for the number of times we're going to pop and push from the heap is going to be n times how many variations of that value we had. So n times log m times log n is going to be the time complexity here. Kind of confusing. This is the bigger term, so we pretty much just ignore this one. So this is the time complexity. Memory complexity is big O of n because of the size of the heap. If this was helpful, please like and subscribe. If you're preparing for coding interviews, check out Leetcode.io. It has a ton of free resources to help you prepare. Thanks for watching, and hopefully I'll see you pretty soon.